All right, guys. Anybody? A few more people just joined. Anybody have questions from anything? Maybe stats related would be good.
Still confused about number 6. I know it has the extra part in the equation that's the only reason why I put no, but I don't know how to explain why.
So there's two different levels to this. The easy level is definition level. The definition of a linear function is one that can be put in the form y equals mx plus b. And you cannot do that with this because, like you just said, there's their extra piece, right? You can't make it mx plus b because it's got an extra x squared thing. So on a definitional level, that does answer the question, right? But what I just said to Alfonso, I think it was Alfonso I was talking to, if the minute you get something like x squared, 2 squared is 4, 3 squared is 9, that's gone up by 5. 4 squared is 16, that's gone up by 7. So every step you take, it is not increasing at the same amount, is it? That's why it's curving. So that's the more technical reason why, if you have something that's not to the first power, the slope is not going to be constant. It's going to be increasing by more and more and more as you go on. A straight line is supposed to increase by the same, over, up, it's supposed to increase by the same amount. Okay, so either level you want to answer it at is fine. How's everybody else? You guys doing okay out there? Are you as tired as I am? I'm tired. You're like, I don't know, Jeff. I don't know how you feel, man. I know I'm tired. All right. No questions? Okay. What's happening in a week?
A quiz.
A quiz. There you go. Cool. Chapter 12 quiz. What's happening in 2 weeks, in 2 days?
Our final exam.
Final exam. So what I put up on Canvas, let me go ahead and show you guys. You don't have to worry about this yet. And I scared somebody into thinking that it was sooner than it is, but the final is on June 2nd. And if you go modules, and let me become a student, and you go down. Oh, I made it the very first thing. Practice final, pop. There's a practice final. Pretend it's here. It's behind this circle of death. There we go. So there's a practice final. Look at that. Oh yeah, that's a nice long one. Yeah, buddy. All right. Sorry. And of course, I'm going to put up what do you call it? Solutions video for that. I actually created it 2 semesters ago, so I'll put that up there, and we'll all look at Jeff from 2 semesters ago, see what he was doing. I think he was more sane. I hope he was more sane. I don't know. All right. If there's no questions from anything, we're just gonna, let's see, does anybody need to do another example from chapter 12 for the linear correlation stuff? Yes? Okay. Let me see if I can, let's see, what do I have here? Can I find some real quick, or do we just want to make something up? Let me see if I can find something real quick. I know what I'll do. Everybody just hang tight. Let me see here. Let's see. Where are you? That's not good. Hold on, everybody. Hold on to your butts. All right, let's see. Trying to find a good example here, or I could just make one up, I guess. Looks like I'm gonna have to make one up. Dadgummit. Rawr. All right, we could do the one from the practice final if you want to. Does that sound all right? No, I should probably leave that one alone for you. I should probably leave something for you to try. So let me make one up. All right. So you can't stand up, Jeff? Yeah, I guess I can stand up. All right. Let's say I've got this data here. What do you got, Jeff? Oh boy. All right, let's see. What can I make up all of a sudden? Hours practiced, golf score. I like it. This will be good. Hours practice, let's say 10, 14, 16, 25, 26, 38. All right. So far, so good. And then let's say golf score. I don't know. What's golf? Oh, yeah. 92, 80, 81, 77, 75, 71. Sure. All right. It's a little bit off kilter, sorry. So what I want you to do, put this in your calculator, find R, interpret R. Find the line of best fit. And then graph the points and the line. I have to be able to do all of those things for the quiz and for the final. Let me do that too at the same time here. Do. All right. Shoot, where is it? It's not here. Damn it. ¿Dónde está? Oh, crap. I don't know what it's called. Darn it. All right, let's see if I can find this real quick. There we go. Everybody doing okay out there? You should have your data in the calculator by now, right? Has anybody gotten to the point where they figured out what R is? Okay, hold on to that. So let me just show you what I did here. Crap, hold on. I'm opening all kinds of weird things. All right, here we go. So I've got the data in, boom, boom. Then what do I push to get the line of best fit and the correlation coefficient? What's a good button to say if you don't know?
Stat.
Yeah. So once you hit the stat button, hopefully once you get in here, you're like, oh yeah, I go to calc. And then of course I pick number
4.
4. And again, I told you if you want to, you can put this here. I'm just not going to do it right now. Let's see. So what I get this. Do those match up with what you got? Anybody? Okay. Is anyone not able to get those numbers? Yeah, what the hell does R mean? What does this mean? All right, let me tell you a little bit more of the story. Okay, 2 things I want to show you. So everybody got these numbers? Anybody not get these numbers? And again, what's the slope of the line of best fit? Anybody?
92.68.
That's the y-intercept. Careful. So the slope is the A, 0.62x plus 92.68. R is negative 0.89 basically. And then we got to work on this one. We got to interpret R. So let me show you. I'm not going to give you this table. I just want to show you that it exists. Yeah, where's everything in the world? Here it is. Look at this weird ass table. Look at this. Just gaze upon this. All right, let me zoom in a little bit. How big of a sample do we have up there? How big of a sample is this? What's happening? How big of a sample is this?
Are you talking about the one that you gave us?
Yeah, this problem. The problem we're working on.
6.
6. I like it. Talk to 6 people, right? So now, I'm sorry. I don't know. I'm pointing to the board. It's very tiny for you, but you should be able to look at your work and tell me it's 6. I talked to 6 people. So look at 6 here. How big does R have to be for like, ooh, this sounds, see how I can make this a hypothesis test? Doesn't it have to be 0.811, or in this case, negative 0.811? Did we get closer to -1 than 0.811 negative? Are you guys able to handle this? R is negative 0.89. Is that closer to -1 than negative 0.811? Did we get far enough away? So I'm going to tell you, okay, I don't know what's happening today. All right. So on a test or a quiz, I'm going to say R has to be greater than this, or R, in this case, I would say R has to be less than negative 0.811 to show evidence of correlation. Did we find evidence of correlation?
Yes.
Yes, we did. I like it. What if I wanted to do it at the 0.01 level? Would we have found evidence?
No.
No, we wouldn't have been far enough away. Is 6 a very big sample?
No.
No, so no. All right, so we did find correlation. We found negative correlation. In this case, I would still say it's actually kind of weak because we just barely got above this. If it was a much bigger sample, if I had to be above 0.396 and I got 0.89, I'm like, that's strong. All right, I don't know. So again, I'm going to make it more definitive on the quiz and the test. So you're not having to figure out what adjective to use. It's mildly strong with hints of weakness. No, all right. So you're never going to see this again. Okay, watch. It's gone from your life forever. But I just want you to know that it exists. And that's where I'm going to get the number I'm going to tell you. R tells you how strong the relationship is between the line and the points. The closer R is to -1 or 1, the stronger the relationship gets. If R was -1 or 1, that means perfect correlation. Okay, all right.
What's the difference between if it's negative or positive?
Downslope, upslope.
Okay.
That's all. Yeah. Let's see what else I was going to say. Oh, I want to tell you one more thing. And again, everything I'm telling you is sort of like just giving you a fuller picture. It's not necessarily something you're going to have to worry about. So for example, why does this thing tell me R squared? It seems kind of dumb, but here's what it is. You ready? I'm going to say this maybe twice at most. 78% of the changes in Y can be explained by the changes in X. So 22% of the changes is explained possibly by some other variable, some other factor. So I'm looking at hours practice versus golf score. What about if both of your parents played golf? Wouldn't that affect maybe something, maybe genetically? What about access to good golf resources early age? Or what about age that you started playing golf? What about, so aren't there other factors besides how much you've practiced that would go into determining, you know, why you do so well at golf or do poorly? Yes, maybe, yes. What about number of beers you had the night before you had your golf round? That might change. So there's R squared sort of gives you an idea of the percentage of the differences in Y that the changes in X change. So 78% of the changes in the golf scores can be explained by the changes in the hours practice. Are you ever going to have to say that to me? Never. I just want you to know. I just want you to know there's a reason R squared is given to us. Okay. Man, I'm tired already. How much of class is there left? Oh, there's a lot. Okay. Now, how do I graph this thing? Whatever. If I hit graph, this seems very, oh, geez. I got a little smudge there. It looks like it was some weird bird having some troubles. I don't know. Sorry, look like a little bird poop. So how do I see my data? How do I see my line? Where do I go to get the line in there? The line of best fit. Where do I go?
You go to the Y.
Good. Oh, I got, okay. Mine is in weird stuff for my, hold on. All right. Mine is in weird form for my pre-calculus class. So now we put in here negative, what was it? Negative 0.62x plus 96 point, was that it? 96.8? 92.68. So close, Jeff, yet so far. Okay, 92.68. And now if I still hit graph, I don't see much anything. I don't even see my little smudge anymore.
What should I do if my graph doesn't work?
What, are you getting an error?
Yeah,
What's it say?
it says error syntax.
Does it say go to?
Yes.
Hit go to, and the cursor should show up on what the problem is. Is it a negative sign?
It just shows the y equals thing.
But where's the cursor? Yeah, it's the negative sign. So Do you see how there's a minus sign and a negative sign?
Oh,
Yeah.
yes. Okay.
Now, I still don't see anything. What have I forgotten to hit? Zoom? Zoom stat. I like it. Bam! There it is. And you can see why it's not like the strongest thing in the world. I mean, that's kind of far away, right? But it's not that bad. So this is what you would have to take a snapshot of and turn in with your quiz and your final exam. I need to see this, your data points and the line of best fit. All right. Is that all right, guys? So you have to be able to do everything we just did on your own. Okay. And relative to some of the other stuff we've done, it's not too bad, right? Okay.
Wait, sorry. How do I plot the points?
Well, all right. If you hit Zoom 9, what happens?
I got it. I think. This is what it looks like.
Whoa. All right. So you have chosen. So you're going to have to go to second y equals. Whichever one is turned on, you've chosen this thing. You want to just choose this thing. I'm almost certain that's what happened. Is the correct thing highlighted?
Now it is.
Was it the second one?
Before, yes.
Aha.
Okay. Is that right?
Yeah. Bam. Okay. Everybody else okay? All I am saying is give math a chance. Okay, let me stop sharing. Okay. Anything else about chapter 12 before we step back into bankruptcy? I mean, chapter 11. All right. And again, we're almost done, guys. We're almost done. The light at the end of the tunnel is not a train. It's the actual, we're almost done. Some of you guys will never have to see me again in a few weeks. Yay. Okay. So we're going to get back into, well, actually, we're going to step into chapter 11 for the first time. So chapter 11, I didn't mean to make you trepidatious about this, which is a great word. The fact that I skipped it. I didn't skip it because it's crazy hard. I just skipped it because it does introduce a new chart, right? So we've got the Z-score chart, we got the T-score chart, and today we're gonna have a third chart. We're gonna be given a third chart. So what the hell is this gonna deal with? Okay, so here we go. I'm gonna talk about the idea behind it. We're gonna focus on the technical ways to read the chart, and then we're gonna do an example of what this distribution is used for. So we are gonna talk about a new distribution, okay? And I really wanted to make a ton of sense as to why we need a new distribution. Let me see, my poor little, here we go. Camera does not want to work. There we go. Okay. Get up there. All right. So what if, let me see if I can do something here. All right, what have we done? What are we able to analyze, like hypothesis tests? What kind of things have we done hypothesis tests for? What kind of statistical things? And have a hypothesis test for what? You can do it. I can have a claim about good, exactly, means and percentages. And for both of those, I can calculate a kind of standard deviation, correct? Or I'm given a kind of standard deviation, or in terms of percentages, I can always make my standard deviation. Everybody with me? And of course, if the n's greater than 30, or if NP and NQ are greater than or equal to 5, then I know that it's normally distributed. Stay with me. So both things essentially boil down to using the normal curve. All right, now, what is it about standard deviation and the normal curve? So do these two normal curves have the same standard deviation? No, of course not. Which standard deviation is bigger?
The top one,
The same scale. Sorry, go ahead.
the top one.
Top one's obviously bigger, right? Because it's more spread out. So standard deviation is a measure of how spread out something is. Standard deviation governs the shape of the normal curve, correct? Skinny, more spread out. I like it, right? Pre-COVID, post-COVID. All right, as we go, sorry. It's the reality for a lot of us. All right, so what if I had a claim like this? I claim the standard deviation of grades in this class is greater than 10. Okay. Do you understand the fundamental problem I have? Because now I need to have a distribution of standard deviations. So the standard deviation doesn't make sense, because now there's multiple. So before, I really want you guys to understand this. So hold on to that, come back. When I talk about a test of means, this distribution is where all the sample means are. If this is the real mean, I could have a sample mean here, I could have a sample mean down there, right? And most of them would be in here. Let me stop for a minute. Are you guys all with me? This is what it means when I'm doing a test of means. I have the claim mean, and then this is where all the sample means would show up. And that's why if I find one that's down here, that is really, really unlikely, because they should all be in there for the most part. And what governs the shape of this is the new standard deviation. Yes? So I really want this understood. I cannot use the normal curve that isn't the shape that all the standard deviations would take on. So if I found all standard deviations of samples, what shape do they take? I know that if I find all the sample means, they take on a normal curve if n is greater than 30. Yes? I know that if I take all the sample percentages, as long as NP and NQ are at least 5, I know that they take on a normal curve. Yes? What if I take all the sample standard deviations? They cannot, they're not going to be in a normal curve, because then what the shit? There is no standard deviation for that. I want to see what shape the standard deviations take on. They're going to take on a different shape. Standard deviation tells me what these are shaped like. I need the shape of standard deviations. All right. Hopefully I've made this point. I cannot use a normal curve if I want to know how the standard deviations are distributed. I don't know if you guys are with me or not. You're like, keep going, Jeff. Okay. So the shape. Oh, let me do this. I like this comparison between what we've done before and what we do now. When I'm talking about normal curves, what formulas have we used to find locations in here? What do I mean? So for example, here's the most basic one, right? Is that the only formula we've used that goes along with normal curves? No, what's another one? Let me start it off. You don't like it. We know you're gonna do it, Jeff. Just do it. Does this look familiar so far? No?
And PQ is on the bottom.
Almost.
Squared, or yeah, square root.
Remember the ends on the bottom? And again, remember, this is what we stole from the confidence interval stuff. Let me stop for a minute. So hopefully these, and of course, the only other one is sort of like this one. It's the X bar minus the mean divided by the new standard deviation. It's basically the same thing, right? Are you guys all of these, and there are more. Remember, there's even this one, z equals X bar 1 minus X bar 2 over square root of sigma, let's see, S1 squared over N1 plus S2 squared over N2. Oh my God. All of these can fall into this shape. Okay, now, what about standard deviations? If I take all samples of whatever size, find the sample standard deviation for each. What shape will that take on? Well, here's the thing. All right, I need to have some, so there is a formula for this, but let me show you one of the main formulas for this. Yeah, all right. One of the main formulas we use, and that we're going to use eventually, but not right off the bat, is this one. So for every sample standard deviation I get, if I do this, square it, multiply it by the degrees of freedom divided by the population standard deviation, I'm going to get something equivalent to a z-score, but we decided to call it something exceptionally weird. We decided to call it chi-square, a funky X, and it sounds like it's talking about Dragon Ball. It's not talking about Dragon Ball. I'm sorry. No King Kai. It's actually spelled C-H-I. So this is called chi-square or chi-squared. I don't need you to understand every little detail, but this is the equivalent of Z. This is a possible formulation that talks about how I can change a sample value compared to the population value. Do you see that? Compared to the population value. Do you guys start? So is it the same format? No. Why is it exactly this, Jeff? Take higher level stats courses and they'll tell you. And we'll talk then. Okay. But so now think about this. Can somebody tell me what's the smallest S could be? Considering what S represents, what is the smallest? Can S be negative? No. You guys with me? Because S is the spread. How do you have negative spread? Right? You have to. So what's the smallest S can be? What's the smallest amount of spread that a data set could have? Could a data set be all the same numbers?
Yes.
So then what would the spread be if all the numbers were the same?
0.
Beautiful. So the smallest this value can be is 0. So there's a difference between this and Z. Can Z's be negative? Yes. Can chi-square be negative? No. And I really want you to understand, it's not just because of the squares. The squares definitely kind of reinforce that it can't be negative. But even without the squares, it could not be negative. Standard deviation can't be negative. All right, so one thing that's going to be different is 0 is going to be a hard wall in this guy. Whereas here, 0 was the middle. Here, it's going to start at 0. So here's what it ends up looking like. Okay, this is interesting. So it ends up looking like that. I affectionately call this the Jabba the Hutt distribution. If you've never seen Star Wars, I don't understand you, and you don't understand this reference, but that's okay, right? You don't have to, and I won't say that again. Get out of there, Jabba. Stop it. You and your tongue. Get out. All right. So if you think about this, most samples will end up having there's chi-square be this. The most samples should be close to this. Do you guys kind of agree with me? Most, if you take a sample, a random sample from a population, its standard deviation should be somewhat close to the real standard deviation. Somewhat, it would be so. But and the smallest could be 0, but it could go crazy big. It could vary. If I took a sample of people, can't I pick like a 1-month-old and a 98-year-old? So couldn't the standard deviation be huge if I took a sample? Of course it can. So that's why this goes out here for a long time. Big old long ass tail, right? So this bad boy is skewed right. It's like I pulled the taffy this way. Okay. Now, how much do I want to say about that? I think it's a little technical. Well, maybe I'll bring it up when we look at the chart. There's an interesting connection between this and z-scores, but we'll see that in a minute. Let's do this. Let's see. How do I want to? Yeah. All right. Let's do this. So, much like the t-score chart, this bad boy is going to depend on the degrees of freedom. Right? And it's going to depend on the amount in the tail or tail. So it does depend on what kind of test we're doing. So let's try this. Let's say I have, yeah, well, let's do this. Let me do it on the computer. It might be easier if I do it all in one place. All right, come here. Yeah.
Clarify, you said it will always be skewed to the right, correct?
Uh-oh, I can't really make you out. Say it again. You're coming through a little bit choppy.
Did you say it will always be skewed to the right? Is that correct?
It'll always be
Skewed to the right.
skewed to the right, except for degrees of freedom of 2. So I'll show you the picture in the book, maybe. There's one situation where it doesn't look like this, but that situation does not happen that often. But let me see if I can find that picture real quick for you. Here we go. Perfect. Theirs is a little more boring, but oh well. So degrees of freedom of 2, it looks like this. It looks exceptionally weird. And that's such a small sample size, right? So this is because it's much, much easier for a sample size of 3 to pick the same data point over and over and over again. So it'd have a 0. So that's why the 0 goes way up. Let me see. What was the other thing I was going to show you? I can't remember. Most of the time it looks like skewed to the right, although this is really hard to see that's happening. This is a little bit easier, I think. Skewed to the right. All right. So what was the other thing I want to show you? Oh yeah. I gotta unblock this. Hold on. There is the chi-square chart. I'm gonna unlock it on Canvas. Right. Oh, I did already. Oh, sweet. All right. So if you go on Canvas, you will see this chi-square chart. And look at that. Just look at that. Just soak it in. It's just amazing. Just amazing. Maybe I should try. I've never tried this. Let me try this real quick. Let's see. You gonna do it, Jeff? I don't know. All right, let's try it. Let me stop sharing. I want to try something with you guys real quick. Let's see how this works. I'm excited. I've never thought about doing this until just right now. All right. Put this back up here. So here's a set of data. All right. Can you pick 3 numbers off of this data? Pick 3. And then figure out what the sample standard deviation is. You can do that with 1 var stats, correct? While you guys are doing that, I'll figure out what the whole standard deviation is. So everybody pick 3 randomly selected data points. Jeff, really, is it that hard to figure out how to move your hand? 3 randomly selected data points from up there. Oh man, my batteries are almost dead. All right, it's too bad, Jeff. Now, let me see. See if I can sneak this in real quick. Oh, I better write that down before this thing dies. All right. Has everybody got that going? Shouldn't take forever, right? You just got to put 3 numbers in your calculator. All right, in your calculator. I get this. All right, so now watch what I'm about to do. So everybody, let me know if you're having trouble. If you're having trouble, let me know. I picked 3 numbers and I got a standard deviation of, this is mine, don't steal mine. I got 8.386. Some of you guys might have gotten very much bigger than that. Some of you guys might have gotten smaller than that. Everybody with me? Everybody should get something different. There's a chance that you pick the same numbers as somebody else. That's fine. Did anybody else get this? Okay, all right. Now, I'm going to calculate my chi-square. 1, 2, 3, 4, 5, 6, 7, 8. So that's 7, correct? 7 times my standard deviation squared. Now, I'll tell you this, sigma is 11.054. That is the standard deviation for all of it, correct? Jeff, hello. All right, let's see. I'm real curious. Does everybody understand? I want you to do the same thing. So in here, this is going to be the one thing that's different for you. It's going to be your standard deviation that you got for the 3 numbers you picked. Oh, calculator, don't die. Don't die yet, calculator. I've got to find my, oh, this is squared, by the way. Dadgummit, Jeff. Come off of there. Ah! All right. Oh, you're gonna die. All right. All right, I got something. All right. So I got 4.029 for my chi-square. That was my chi-square. 8.36. Okay, I like it. Bum, 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 bum. I'm making a few assumptions here, and that's just the way it's got to be. Could anybody, is everybody doing okay? You have any questions about what's, was everybody able to figure out an S? You just had to pick 3 numbers, put it into the list and do 1 var stats. Is that all right?
I have a question.
Yes.
So, for the data, N, so since we picked
3 numbers, would our number be 2 or would it be like 7 because we're doing all of that data? Because you said to pick 3 numbers.
Oh yeah, I did. Why did I put 7? All right, thank you. Let me change this up. So yeah, our sample size was 3, so this should be 2. Thank you. And then, all right, what would this be, Jeff? You can do it, buddy. Nothing too crazy. All right, that was my mistake. Thank you for catching that. I was being silly. So I got 1.151. Yeah, so this should be 2 because our sample size was 3. We took a sample of 3 numbers. Okay. All right. Has everybody discovered their S? Did everybody get their S? Okay. And then all I got to do is 2 times your S squared divided by 11.054 squared. 11.054 is the actual standard deviation of all of those. Who thinks they got the largest value of their standard deviation? Who got something bigger than 8? Anybody? Are you guys all playing along with me? Are you guys all there? Somebody must have.
16.
Beautiful.
58.
Thank you. Anybody got something bigger than 16? All right, so 16. Let's see, what would that be? That would be roughly that. Okay. All right. All right. I like it. All right. Now watch. Now let's look at this chart again. What's the degrees of freedom? What's the degrees of freedom? It would be 2, right? N minus 1.
7.
No, that was my mistake. It's 2. It's 2 because our sample size was 3. So if you look at this row, what this tells me is, all right. So the way to read this chart. Come on, Jeff. Yeah. What are you? All right. So much shit over here. Where's my pen? There you are. All right. Am I picked the right place? Probably not, Jeff. Let me see. No, you haven't. Hold on, everybody. Hold on to your butts. Here we go. Let's see. Where are you guys? There you are. Oh, I'm so ready to not have to do this with all this stuff, canvas and everything. All right, now watch. So what this means is that for this problem, I am kind of assuming that it's normally distributed. That's all right. 90. All right. So see how it says area to the right of the value? So this one would be right there, 0.016, because the area to the right of it would be 90%. All right. So that's one thing that's very different. Okay. This chart is a little evil because every chart we've had before this have either had it in the tails or they've been to the left, like the z-score charts to the left. This one's to the right. Too bad. So if you got a chi-square value, no, Jeff, you're looking at the wrong row, buddy. You're doing a great job, Jeff. Doing a great job, kid. Be quiet. All right, so we're looking at this row. If you got a chi-square above 0.211, then you're in here, right? If you got a chi-square below 0.211, then that's only a 10% chance of happening. Did anyone get a chi-square below 0.211? No. And I think the person that got 16 something or other, what was your chi-square? What did it end up being? I think somewhere in here, right? Who got above? Who got 16 for the standard deviation? Somebody did. Did I dream that? Did I have a waking dream? Who got the largest standard deviation? Somebody spoke up earlier, didn't they? Or is that? Am I awake now? Yeah. Didn't somebody? No? What happened? All right, fine, be that way. But if somebody did get a 16 or so standard deviation, they would have fallen in here. They would have had 4 point something or other, right? Only about 2.5% would have a higher one than this. All right, I don't know if you guys, all right, maybe this is a bad idea. Did anyone, all right.
I got a 12. I got 12.77. It wasn't 16, but mine was up there.
What was your chi-square?
I got 3.00, so 3.
3. So you're in between. I'm looking at the wrong thing over here, Jeff. You keep looking at the first. All right. So you got. What'd you just say? I'm sorry. You got chi-square was what again?
3.00.
3.00. So you got in here 3.00. So you're right in the heart of things. You're right in the heart of everything. So you're about where at the upper edge of what we would expect. So if somebody got like a 4.6, which I think is roughly what this would have, the 16 would have gotten, that means that they're at the 10th, like they're in the top 10%. Go ahead, sorry.
I got a standard deviation of 15.87.
15.87, and your chi-square was what?
4.122.
Sweet. 4.122. So you're like right below this. So you guys are like up here, where you have only like 10% above you or so roughly. All right, so this is like most of us, I would expect that most of us would fall between 0.211 and 4.61. Because that's right in the heart of everything. That's the heart of it. That's where most of us should have been. And it sounds like that's where most of us went. Who thinks they got the smallest value? Anybody? Did anyone get a smaller chi-square than, what did I get? 1.151? Or was mine the smallest? Okay, all right. Now, something I didn't say is that you could have picked the same data point twice or even 3 times. Because when we do this, we do it with replacement. And remember, we talked a long time ago about why that's true, because otherwise it really screws up all our probabilities. All right, let me stop this. Please, Jeff, stop this. Okay, I got to refine that a little bit. Like I said, it just came to mind. I've never actually done that with the class, but I kind of like that. I just have to refine it a little bit. So that's my, thanks for being my guinea pigs. Let me see. Now, let's get into the first type of distribution that uses a chi-square. So what was the first kind of problem that we had that used a normal distribution? It was just figuring out the probability that somebody's average was more or less than something, right? And there had to be certain specifications that it met. It had to be, I had to know it was normally distributed, so in order to do it. So let me stop sharing this real quick. Get out of here. Oh, okay. So we're not going to get so, there are requirements, but we're not going to get so deep into those as to when I'm allowed to use chi-square thing. It gets a little bit strange, but we are going to jump into a really cool thing. So for example, let me paint the picture here. Let's say that I expect the grades for my class to follow a normal curve, right? Let's say, well, let's see, is there a better one to start with, Jeff? Yeah, let's start with a different one. That gets a little weird even. Let's start with M&Ms. Does anyone eat a lot of M&Ms? Does anyone eat some M&Ms? Everybody's eating some of them. Do you think that there are more of one kind of color than a lot? Oh, Anthony eats a lot. Anthony, you're going to be our resident M&M expert. Do you think that there's any color that shows up more than other colors? You know what I mean? The colors that you can get in M&Ms. Or do you go to the M&M store and get specific types of colors? Do you control your colors, or do you just get an M&M bag and just accept the colors as they come? I don't know. Oh, weird. So it depends on the bag. Okay, that's interesting. Now, just stay with me. Let's suppose that we had the claim that the colors are evenly distributed in all bags of M&Ms. Is everybody with me? So that's a claim. All the colors are evenly distributed in the bag of M&Ms. Can you stop and realize that there's no freaking way we can do that in a normal hypothesis test like we've done? Do you guys understand? Am I saying a percentage is greater or less than some other percentage? Am I saying an average is equal to or less than or greater than some other average? No, I'm saying the colors are evenly distributed in all the bags of M&Ms. That is a different claim than we've ever been able to handle. Are you guys semi with me at all? Do you understand that definitely does not fall into any hypothesis test we've looked at yet? And I know you're all getting antsy. You're all like, more freaking hypothesis tests, Jeff? Are you kidding me? That was like 1/4 of my life in this class. Yes, I know. So we're not going to do the full hypothesis test. I'm going to be a little more lenient on these. All right, so this is called a goodness of fit test. We want to see how well does our observations, in this case, if we got a bag of M&Ms and poured them all out and somehow had the willpower to not start eating them and instead just separated them into their colors. Did anyone do that when they were a little kid? Separate them into their colors? No?
That was Skittles.
Skittles, okay, same idea, but never mix Skittles with M&Ms. That will have to hurt you if you do that. Now, if we, I didn't call it for another, okay. If we do that, if we get a bag and we put it out and we look at all the distribution, I want to compare that somehow. Stay with me. For example, if I thought that the mean was 11 and I take a sample and I get the mean of that sample is 10, do I stop there and say the mean is not 11? If I think the mean is 11 and I take a sample and I get a mean from the sample of 10, do I just stop and go, well, it's not 11? You know better than that. Why is that? Why can't we just stop there? Crystal, I'm sorry. You're still like really choppy. I can't. Okay. I think you said it's just from a sample. Good. Okay, that's part of it. And other thing is the whole thing is it's got to be far enough away, right? It's just a sample. You can't prove shit directly. It's just a little sample. So not only does it have to be different, it has to be very different. It has to be unusually different. It has to be more than 2 steps away or whatever the alpha leads to. Okay. Now, please, Jeff, give me something concrete before I go and say, okay. So there is a, let me make this one active now. We might as well do this straight off of the, yeah. So I'm going to make another sheet active in unit 11, bam. If you go to Canvas, there's a goodness of fit correlation. Oh, I don't know why I put correlation on there too. Oh, duh. That would have been good. Oh, well. I forgot I have this. On the other side of this, there's a whole correlation problem. Look at that we could have done earlier. Oh, well. Good job, Jeff. Pass. Oh, shit. This is done. All right, let me stop sharing. All right. Ooh. So don't look at it. Don't look at it. I forgot that I had that problem completed. All right, so let me see. Let me do this. So where did it go? There it is. Okay, now watch. Let's say I get a bag of M&Ms And there are 42 M&Ms in the bag. And we have brown M&Ms. Get in there. We have yellow, red, blue, orange, and green. Okay. All right. All right, stay with me, stay with me. Oh shit, you can't really see this, can you? Somebody can speak up. All right. Now, let's say we observe. There's the observed. So we look at our bag and we see 5 brown M&Ms. We see 6 yellow, 5 red, 10 blue, 9 orange, and 7 green. Now this better add up to be 26. Thank God, it adds up to be 42. Now, if I was testing the claim that they're evenly distributed, how many would I expect of each color? You can do this. How many of each color would I expect to see? There's how many colors do I have up here? 6. And how many total M&Ms do I have?
42.
So how many should show up in each color category?
7.
Yes, because the assumption is it's evenly distributed. It's uniformly distributed. Remember those? Remember uniform distribution? Okay, Jeff, whatever. It's fine. All right. So I would expect, given the claim, I would expect there to be 7 of each. Now, why can't I just stop and go, well, there's not 7 of each, so it's shit. The same reason I can't stop if they say it's 11, I get 10, I can't stop. I got to keep going. Is that good enough? Is that enough evidence? Is this, it's different, isn't it? Isn't it different? Is it different enough? Is the question. That is the question. Now, let me see if you guys will agree with the formula that happens. What immediately makes sense to do if I'm trying to measure how different these are? How can you tell these are different? Because how many brown are there? Are there as many brown as there's supposed to be? If this is true?
No.
How many fewer are there?
2.
There, see, so shouldn't I take a difference? And maybe I should square that difference also. Remember the lesson we learned way back when we did standard deviation, we had to square shit because some of it was negative. I don't want negative M&Ms. I don't want to think about what that means. -5 M&Ms, what does that mean? I don't want to think about it. So let me do observed minus expected squared. That will give me a feel as to how different these guys are. So 5 minus 7 -2 squared is 4. Oh, Jeff, you suck at making grids. I know. Leave me alone. 6 minus 7 squared is 1. 5 minus 7 squared is 4. 10 minus 7 squared is 9. 9 minus 7 squared is 4. 7 minus 7 squared is 0. Now, the last thing I'm going to do, let me see if this makes sense. If I had 3 cents and you have $1.50, aren't those relatively different? Those are pretty different, right? let me see if I can say this in a different way. All right, if I had $1 and you had $10, do you have a lot more money than me? Yes, you have 10 times as much money as I do, correct? You guys with me? If I had 1,000,001 and you have 1,000,010, is that very different?
No.
Hell no, right? Are you guys with me on that? If I had $18,000,001 and you had $18,000,010, I'm not gonna go, damn it, you beat me. No, I have freaking $18,000,000,000. Who gives a shit about one? If all I got to my name is $1 and you got $10, I'm like, wow, man, watch out. You know, if we were little kids, I got $1 from the Tooth Fairy. You got $10 from the Tooth Fairy. I'm like, what do your parents do? No, because I don't know. I think it's just the Tooth Fairy. Tooth Fairy doesn't like me. Anyway, sorry. Stay with me. So this difference, I want to make it a relative difference. So what I'm going to do is I'm going to divide it by the expected. I'm going to divide by the expected. Just to give me an idea of how relatively different it is. So 4, oh shit, what's 4 divided by 7? Good job, I think I have an answer there. There it is.
Is it O minus E squared divided by E? Because I can't really see the top of it. But.
I'm sorry.
No, it's okay. I was just asking to make sure.
Oh, I see. Somehow I got all off kilter. There we go. And then 1 divided by 7 is 0.143. 4 divided by 7, I already did. Oh, this is exciting, Jeff. I can't even contain myself. 9 divided by 7 is 1.29. Yeah, 286. And then 4 divided by 7, I did. Oh my goodness. And then 0 divided by 7 is 0. Now, of course, if these were all 7s, wouldn't these be all 0s? And then these would be all 0s, correct? Yes, okay. I can't make the number 5 for some reason. There we go, Jeff. Now, can somebody real quick add these up for me? Seven, 3.202. I don't know. 3.143. I got it close. It's 3.143 if you add those all up. You guys agree with me? I don't know. You just have to add them up.
Yeah, I got 3.142.
Okay, cool. I probably left something out. 7, 8, 9, 2. Yeah, it should be 2. Where do you get 3 from? Oh, I probably in the background didn't round so much, but I agree with you. 3.142. Okay, now stay with me. Stay with me. This is related to the idea of Z star. This is related to this. This gives me an idea of how far away from 0 I am. What would it mean if all these were 0 again? I just said it a minute ago. If everything was 0, what would that mean? What's the only way for this to come out 0? What's the only way this can come out 0 is if these
the same.
Are the same. And if all of these are the same, didn't it come out exactly as you expected it? So if you get 0, that's really good evidence against the idea that it isn't uniform. Okay. So now what I'm doing, all right, I really want this to make sense. All right, so oh, look at that, that's neat. I don't know what that is. So here's the idea. I've got my distribution. I need to figure out where enough evidence, not only here's 0, 0 would mean it's exactly what I expected. How far do I have to get away until it's evidence that it's different. So this means the same. This is more and more and more and more evidence until you get to good evidence. This would be good evidence that it's different. Really, 0 means no difference. They're exactly the same. How far do I have to get before it's evidence that it really is different? Oh, shit. Oh, shit. Are you guys still with me? You guys hate this. Stay with me. Okay. So watch this. If somebody tell me how many categories are there? 6, right? All right, so for this kind of test, the degrees of freedom, I think you're going to really love this. They spell categories with a K. They don't really, it's just the letter we use, but degrees of freedom is the number of categories minus 1. So this will be 6 minus 1 is 5. So the degrees of freedom for a goodness of fit test is the number of categories minus 1. It's not 42 minus 1. It's how many categories minus 1. All right. This, what we just did here, that is the formula for the chi-square. That is a second formula for chi-square. Why does that not concern us? Because we had at least 4 formulas for z-scores, didn't we? So we understand that there's different formulas for the same shape. So here's another formula for chi-square that I use for these goodness of fit tests. Now, degrees of freedom is 5. Stay with me now. I've got all of this on this thing. Don't worry. Don't worry. It's gonna come together. I just gotta, oh gosh, where's my crazy ass? Oh, chi-square chart, where'd you go? All right, here we go. So degrees of freedom is 5. I'm sorry, alpha, let's say, is 0.05. And degrees of freedom is 5. So what is the critical? Where does enough evidence start? Not only do I have to not be 0 to show evidence that they're different, I have to actually be past 11.071 to show a difference. Did we make it that far? We got 3.142. Did we make it far enough away?
No.
No. All right, let me immediately show you. So I don't know if anybody's already looking at this thing, but here's that goodness of fit. And here's the first problem that I've got worked out for you on this piece of paper. See this? Here's all the work we just did, right? And I think this is because in my calculator, I didn't round. But yeah, you're right. It would become 2 right there if I just use these numbers. Stay with me now. Stay with me. Isn't this the number we just looked up? 11.071? Stay with me. So my sample would have to get that far away to show evidence that it doesn't follow a uniform distribution, to show that it's different from what I expected. The population would be. I know this one bag is, but is that evidence that the whole population is? No, we only made it here. We didn't make it anywhere near far enough away. So I don't need you to do the whole hypothesis test thing at all. You fill in the chart, you figure out your chi-square here, you compare it to the number you're going to look up, and you see if you made it far enough away. Because remember, it makes sense. 0 means no difference. So evidence that it's different would have to be far above 0, because 0 means no difference. Oh, you guys love this. I know you love it. Just keep repeating to yourself, it's almost over, it's almost over. Now, here's the other kind of problem that I was talking about. I was going to get into with the grades. So let's do this problem together. This is a different, see up here, test if the colors are uniformly distributed, which means all of them would have to have the same number. And that's when I divide to see how much one would each would get. Are you guys with me? So it could say test if it's uniformly distributed, Or it could say, here's what cholesterol is supposed to do. Test if these people on this secluded area. All right. Anybody old enough to remember the Mediterranean diet?
Yes.
Or
Not even
just
that old.
knowledgeable about history, I guess I could have said also, because I
Oh,
mean, I
yeah.
wasn't around when the movie Metropolis came out, but I certainly have watched it. Now, everybody thought olive oil, if I just start guzzling olive oil, I'll be skinny like the people in the Mediterranean because they they don't drink it, thank God. They use olive oil all the time. So you had people eating the exact same shit they were eating before, just throwing olive oil on it. This was maybe in the 70s, 80s. I can't remember exactly when it was. Even I was a young thing. I was like, what the hell is people doing with olive oil? I don't know if you guys know about it. And I think there was something about apple cider vinegar or something recently, right? That was supposed to magically make the pounds melt. I don't know. Anyway, so let's say that we go to this island somewhere and we observe these cholesterol levels in the people there. And we're curious, do the people there have different cholesterol levels? Is there evidence that the cholesterol levels don't follow this distribution? Now, here's the thing I need you to think. We talked to 500 people, right? Let's do this first. I don't know why I'm doing it this way. I'm just going to do it this way. That's all there is to it. All right, we'll do it this way. Observed, that's easy. They got to tell you what they observed. So 132 are below 130 and so forth. You with me? 219 are between 130 and 200. 101 are between those two. And the rest, oh shit, the rest, Jeff, I got to add these that way. 3 4, that leaves 48, I believe. Is that right? Hopefully. You guys with me? Everybody see where I got that 48 from? Are you guys doing okay?
It's just a leftover of what of the other three.
Exactly.
Okay.
I think some of you guys are shell shocked. I've dumped a lot on you and I'm sorry. It's just the way things are. Hopefully some of what I've said has made sense so far. I don't know. So here's the key. So that's easy. I have to tell you directly the observations. I have to tell you because you can't see these people. So the problem's got to tell you what's up with these people. Now, how the hell am I going to figure out what goes here? How many should I expect from that would have less than 130 cholesterol level? What do I do? What do I do?
Do 500 minus 132?
Nope, nope, nope. How many do I expect? What percentage do I expect to have less than 130?
20.
20%. So how many do I expect to be here? 20% of what?
500.
500. And of course, 20% of 500 is?
Hundred.
100. So we got 100 there. Let me take these out here. Keep going. What goes here? 150.
175.
175.
75.
75. All right. All right. And the double check, you could add these up and they're supposed to add up to be what?
500.
And they do, thank God. So you can just double check and make sure you didn't lose anybody. There's all 500 people here. Will these always be nice whole numbers? No, because these are not necessarily going to be nice percentages, right? And this number is not always going to be a nice round number like 500, but that's okay. This is just how many is expected, and that could be a decimal number of people, and that's fine. Now, I want you to realize you could actually do this, like this could be L1, this could be L2. This would be L1 minus L2 squared. Do you guys understand? You could do all this in your calculator, and then this would be L3 divided by L2. Do you see that? So that's how you could do it in the old calculator if you want to make things quicker. I think my calculator is dead. Oh, you just died. All right. So I'm gonna have to rely on the kindness of strangers. Let's see. You're not strangers. I know you people. Let's see. What's 32 times 32? It's 900 and that's 1,000. Let's see. 32 times 32. 960. 1,024. Is that right? That sounds right.
That's what I got.
All right, and then divided by 100, that's easy. Okay, that first row was not bad. I think the other ones are gross, so I'm going to need some help. Is there anybody that doesn't understand where 1,024 came from? Or 10.24? Speak now or hold your peace for a little bit. You can always ask later.
Did it come from 132 times 130?
No. So the categories has nothing to do with the math I'm doing. These are just categories. So what's it say to do? What's this say to do? Take the observed minus the expected.
I see. That's easy.
Yeah. 132 minus 100 is 32 and then squared. That's
Okay.
all.
I got it.
Here, 219 minus 150 is 69. Squared is something. 4760. I lost it. 4760 something. Is that right? Is anybody out there help me?
Yeah, 4761.
4761.
I got
31.74.
31.74
Yes.
over there. Let's see. Yeah, that sounds about right. Okay. I don't see anybody yelling about it. Okay. And then 74 squared. Oh shit, here's this 5476.
That's what I also got too in the chat.
And I lost it. 31.29. When you divide those, that sounds about right. And then 75 minus 48 would be, really, Jeff? 27? 27 squared, is that 729? Yeah.
Yes.
Okay. And then 729 divided by 75. That's
9.72.
9.72. So when you add these up, this is going to be insane. When you add those up, you get 62, 72, 81, 82.468, 82.95. That could be really off. Don't worry.
I got 82.99.
99, of course. What did I do wrong? Let's see. Oh, Jeff. All right, I'm okay. 82.99. Now, we haven't done this very much, but do you think that's big? I mean, remember up here we got 3.143. Well, let's see. Let's see. I've got to look up the chi. Where does evidence start? So I'm at a 0.01 level of significance. What's the degrees of freedom?
499.
No. So alpha is 0.01. Degrees of freedom. How many categories are there?
Oh. There's 3.
There's 4.
I mean, degrees of freedom is 3.
Gotcha. Okay. So can you look that up in the chi-square chart? 0.01. Go down until you get to degrees of freedom of 3. Everybody can ask. Sorry, go ahead.
11.345.
It sounds maybe about right. Is that what everybody else got? No? Are you guys all right out there?
Yes.
Yes? Okay.
I have a slow connection right now, so I'm waiting for the chart to load again.
Uh-oh, all right. Does it even matter exactly what this is? I mean, where the hell is 82.99? Where is that?
Way from
Definitely out there. I mean, my God, that's crazy. So 0 means there's no difference. If we make it past this point, what have we shown evidence of? If 0 means there's no difference, and we got way over there, what have we found evidence of? That these cholesterol levels are how related to what we expect? Is it what we expected? Or is it different from what we expected? The closer go ahead.
Oh, I was just gonna say it's different than we expected.
Big time different, right? The closer I am to 0, the closer that is to no difference, at least in my sample. So my sample has to be at least this far away in terms of chi-square, and we got 82.9999. We're way the hell out there. So we found big time differences, right? In fact, you could be more specific. Were these people in a secluded area, were their cholesterols better or worse than normal? Considering that a lower number is better. We're considering this to be the, what is it? UDL, LDL? The bad cholesterol. There's a good cholesterol and there's a bad cholesterol. Here's what we observed for low cholesterol. Here's what we expected. Was that better? Are they better?
Yes.
Yes. Here's what we saw for like the middle part. And then here's what we saw for the higher cholesterol. And here's what we saw for the highest cholesterol. So it seems that we have found evidence that these people have blood cholesterols much lower than what we expect. So wouldn't we want to go in there and do some more targeted statistical analysis to figure out what it is? Or are we all just going to start drinking their bottled water and assume it's the water? Right? That sounds like something we would do in the 70s. Oh man, these people are doing great. Let's drink their water. That must be what it is. Yeah. What kind of oil do they use? No? Okay. Are you guys with me at all out there? So what we do now is we would go in and start to pick apart, okay, where are all the people that eat this kind of nut that grows on this kind of tree? And then we're going to have a control group. These people don't, these people do, right? We'll see if there's a difference in the cholesterol, and we can all do much more targeted testing. Okay, that's enough of that. Enough. Okay. Let's see. What else? Oh, yeah. So right here, what we would say is we have found evidence that the cholesterol level of these people is different from expected. You could even say it's better than expected, but that's a little extra analysis we would do.
Can you bring your screen up a little bit?
Actually, I can't. So let me write it up. I've chosen the worst way to write on things. So we have found evidence that the cholesterol level of these people is different from what we would expect. Oh my gosh. You're gonna have to trust me that that's what it says. We have found evidence that the cholesterol level of these people is different from what we would expect. Like it. So I could do an analysis to see how close a class gets to a normal curve of a distribution of grades. There's all kinds of stuff I could do with this goodness of fit test. It's kind of a weird name. All right. Let me see what time is it. Maybe I've got, well, let's see. Let me, has everybody got what they want from this mess here? Okay. I'm going to stop sharing. Let's see. Whoa. Okay. That was more than I thought I would do. I will tell you this. Let's see. We are going to get into using this formula next, right? Section 11.6. And this is going to be, oh joy, this is where we're going to get back into hypothesis tests. So these will be hypothesis tests of standard deviations. And this would be replacing what we do on our 4-step when we used to do Z star. This would be the formula for our chi-square star, right? So it's going to feel exactly like a goodness of fit test. Stay with me now. A goodness of fit test is a one-tailed test. So what would a two-tailed test look like? Let me see if you guys are still, let me just come right back to the same page. So goodness of fit test is always going to be a right tail test. Goodness of fit will always be a right tail test. In section 11.6, I could have a one-tail test up, a one-tail test down, or a two-tail test. So I could say something like, I think the standard deviation is 3. So then the alternate would be not equal to 3, which means 2 tails. Yay, Jeff, it sounds great. I can't wait. All right. So why don't we wrap that up for today? I think I've hurt your brains enough for today. So what we'll do on Wednesday, we'll do another goodness of fit example. We'll get into section 11.6, and then we'll see how far we can make it. And if we get done with, that's the last section we have. So maybe we can have 2 days of review next week instead of just 1 day. So maybe that's a good thing. All right, that's enough. That's enough for today, guys. So let me know if you need to hang out. Otherwise, you're free to run away.
I did have a quick question.
Yes.
So when you did the example with like where we picked the 3 numbers, you wrote that there was S and then that there was the sigma. What's the difference? Because when we look at when I was looking at when we did the VAR stats, there's one that's the sample.
Oh, so real quick, if you put 3 data points in your calculator, you must pick S because that was just a sample. When I put all of the numbers in my calculator, I picked sigma because that was a population.
Okay.
So you have to know what it is you're putting in your calculator to tell which symbol you're allowed to use.
Okay. Because I was just confused because we used both of those numbers in the formula.
Oh, again, sigma specifically is the standard deviation you would get if you put the entire population in. S is the standard deviation you get when you put a sample.
Okay, so then for that like problem, we use both population and sample then?
But you can't take the two numbers from the one time you hit one var stats. Does that make sense?
A little bit.
Because the calculator gives you both because it's dumb. It's a dumb thing. It doesn't know if you just put a population in or if you just put a sample in. So if you're not putting every single number there is into your calculator, you have to pick S. When I put all the numbers up there into my calculator, I picked sigma because I put the entire population in.
Okay. Cool.
So you can calculate both if that kind of problem is given to you, but to figure out sigma, you got to put all the numbers in. If you don't put all the numbers in, you have to pick the S number because it's a sample now.
Okay.
Okay.
If I have any problems with it, I'll just come back to office hours. Thank you.
You're there. How's everybody else?
I have a question about grades.
Yes. I
Oh,
still have to update them from the last time I did.
Oh, it's because mine says 324%.
Oh, geez. Yeah, that's when I'm not careful with Canvas, it'll start trying to calculate a grade. I've got to tell it not to do that. All right, thank you for letting me know. Yeah, unfortunately, you're not making 324 right now. Sorry. Let me see. So I put in there a while back, I hand put in there the average, your three grades, the average with all homework, the average with no homework, right?
Yeah.
Okay, so I haven't updated those, but now I got to figure out what is it using. All right, I got to figure this out. Shoot. I don't know what it's using to calculate. Oh, 353, what the hell? All right, let's see, what would that be? Maybe the last quiz. Okay, maybe not. What would that be? Is that a 0? All right, it's got to be something recent. So anybody else, you guys okay? I'm going to head out. I'll work on that. All right, I'm out of here. Bye, guys.